Hey, it's Mr. Shrum, and I am back again with a tutorial walkthrough. And we looked at reflecting light last time. Now we're going to look at refracting light. You've seen that when light rays hit a boundary in the medium, they are often reflected back into the same medium. When light rays hit a boundary of another transparent medium, they are often partially transmitted into that medium. So here we have a ray coming in, some of it's reflected back, some of that gets transmitted. And when light rays are transmitted into another medium, they bend. This bending of light is called refraction. Recall that when light rays enter a new medium, their speed changes because the properties of the medium change. It is this change in speed that causes the light rays to bend in the new medium. Note that refraction does not occur if a light ray passes from one medium into the other at an angle of 0 degrees with the normal. So here we have a video, and here you'll observe the behavior of light. You will see how light travels in a straight line and how it is reflected off a surface and partially refracted into a new medium. And as you watch, you can see if you can predict what will happen to the light rays when they are refracted. Once you have watched the video, click next to answer the question based on what you observed in the video. So we have a light ray, and you see how some of it is reflected, and see how the light behaves so interestingly. And I can't show you everything because I might get copyright stricken again. But how did the light beam behave when water was added to the glass trough? Well, if you go back and look at it, the light beam partially reflected and partially refracted into the glass trough. You saw how light is refracted when it travels from air into another medium like glass or water. You also saw how a straight stick immersed in water appears to bend. The apparent bending of the stick in water is an optical illusion caused by refraction. When a stick is placed in water, light travels from air to water, and because of the change in medium, the light bends. Similarly, the light from the stick, when traveling from the water to our eyes, bends due to refraction. We have a natural instinct to assume that light travels in a straight line. So when our brain traces the bent light back into the water, it traces this light in a straight line. That causes the stick to appear to bend near the surface of the water. Just like the apparent bending of the stick, a gannet diver diving into water to catch a fish has to take into account the apparent and actual position of the fish. So what it looks like in the water is not where it actually is. And these things have a natural instinct and possibly the experience to gauge where the actual fish is. So here we have a lesson activity, bending light, this simulation. And in it, you can bend light. Shocker. So here we go. Intro. So here we go. if something hits it straight on, it's there's no bending going on right now. How does the light ray travel after it is released from the laser? The light ray travels through air until it reaches the surface of the water. At the water surface, part of the light ray is reflected back into the air, and part of it enters into the new medium. The light ray then enters, or the part of the light ray that enters the water is refracted and bends toward the normal. So let's go back and see that. If you look here, the index of refraction is 1. The index of refraction in the water is 1.33. And if you look at this, the angles are a little different. Why does the refracted ray bend toward the normal? The light ray is traveling from a faster medium, air, to a slower medium, water. So it bends toward the normal. The angle of reflection of the light ray is always equal to the angle of incidence that I set. It asks you to change the upper medium to water and the lower medium to air and see what happens. Okay. So okay, water to air. So do you see how the angles are behaving differently? Whereas going from air to water, this line that gets transmitted bends towards the normal here. So it would have been going straight like that, but it bent towards the normal. Going from air to water, but from water to air. You see, this would have been straight, but it bends away from the normal here. For any angle greater than about 49 degrees, no light passes from the water to the air. All of the light is reflected. For smaller angles, some light is reflected and some is refracted. This time the light bends away from the normal because it is traveling from a slower medium, water, to a faster medium, air. Let's see what happens when we just put it straight on. The light ray is not bent when the incident ray is along the normal. Now move it to the horizontal position. It is not refracted. So you see how it doesn't even start to transmit until that angle. From water to air. The reflected light intensity from water is about 5.41%, and from glass it's 9.37%. So at this angle, almost twice as much light is reflected from the glass as from the water after you do part G. Part H, finally reset the lower medium to glass and move the laser. How does the angle of incidence affect the amount of reflected light? Support your answer with data. So the light reflects much more strongly when it hits at a larger angle to the normal. At 5 degrees, for example, only about 4% of the light is reflected from the glass. At 85 degrees, about 74% of the light is reflected. Okay. So in the simulation, you saw how a light ray bends upon entering a new medium. The upper image here shows a light ray striking a glass surface at a 90-degree angle. The other image shows a ray incident at an angle and passing through two medium boundaries from air into glass, and then from glass back into air. When a light ray is incident along a normal, it doesn't bend, but rather keeps traveling into the new medium on a straight path. Therefore, the perpendicular light ray travels in a straight line from air to glass and back to air again. A light ray incident on a surface at an angle with the normal will bend when it enters the new medium, and that is due to refraction. So the light ray incident at an angle bends upon entering the glass medium. Because glass is slower medium than air, the ray bends toward the normal. When the refracted ray emerges from the glass, it bends again, but this time it bends away from the normal because it has moved from a slower medium, glass, to a faster medium, air. Note that a light ray that emits from the glass surface is parallel to the incident ray only if the glass has parallel sides, as this does. If you've ever taken a long drive on a hot, dry day, you may have experienced the visual illusion of a pool of water on the road at a distance. This phenomenon, known as a mirage, is caused by refraction of light. Recall that the angle of light refraction depends on the refractive index of the medium. And on a hot day, the air just above the road surface is much hotter than the air higher up. When sunlight travels from the cooler air to the hotter air, the light bends due to refraction because cool air is denser than hot air. Because of the curved light, the road appears to be a little higher than it actually is. And the watery effect that you see is the reflection of the sky on the surface of the cooler air. Pretty neat. And this is a mirage in an African desert. All right, checkpoint time. A light ray passing from medium 1 to medium 2 is bent away from the perpendicular normal to the boundary surface. What happens to the velocity of the refracted wave as it enters medium 2? There we go. Since the angle of the refracted ray moves away from the normal, it must be traveling in a faster medium. All right, moving on to prisms. You've seen how light is refracted when it travels from one medium to another. Now let's explore refraction of light through prisms. This is a prism. It's a solid object with at least one flat, smooth surface that can reflect light. It's generally made of glass, but can be any solid refracting material. And it can often split white light into its constituent color wavelengths. They have a regular geometric shape. The prisms usually found in a physics lab are like the one shown here, with a triangle base and a rectangular side. but I will get into this next time. Bye-bye.